Okay, so today we're going to review stoichiometry, and I'm going to teach you a new technique for doing that will allow you to look at the whole situation at once as opposed to one equation at a time. Now, we're going to call these things BCA tables, and I'm going to tell you what they are for in a minute. But the reason why we're learning the BCA tables now is because we're going to use it for limiting an excess reactant, which is our next concept. So I'm going to teach you basically the fundamental way to do the tables now, and then we're going to apply it to the limiting excess reactant concept instead of trying to teach you all of those concepts in one sitting. So you also will hear them called ice tables, and I'll tell you what those mean in a minute. So BCA tables are basically tabular or graphic tools to look at amounts of materials in a system before, during, and after a process has occurred. So you can kind of monitor it during the whole situation. BCA stands for before, change, and after. You will also hear them called ICE, which stands for initial, change, and equilibrium. Same thing. They're basically the same thing. Before means initial, change, and equilibrium means at the end of the situation. Now, you have to have good skills in chemistry in the following. You have to be able to balance an equation. I keep telling you that. You have to understand how to do molar ratios. We learned that last week. And we have to be able to calculate the number of moles from a given amount of grams, and then vice versa going back. And then we're going to have to be able to do stoichiometry problems. So all the things that we learned last week are going to be applied while we use these tables. Now you're going to say, well, why are we learning another way? Well, there's lots of ways to do things, and sometimes these techniques or different techniques lend information better than others. So I'm hopeful that this tabular technique, which I'm going to show you, is going to be very applicable to seeing you understand this, and also extremely applicable for the excess versus limiting reagent scenario. Okay, so here's how we represent a BCA table. We have a list of things here. We have reactant 1, 2, 3. You could have as many reactants as you want. Product 1, product 2. Again, if you had product 3, it'd go here. So you're going to list all the reactants first and then all the products, right? And we're going to put in amounts before, what the change is after or during the reaction, and then after how much stuff you have left over, if any, right? So here's all the definitions. Now, here's the key thing that you have to remember is that all of our tables, all of the amounts are in moles. Again, chemistry isn't done in moles. So if you're starting out with grams, you need to convert to moles. And you should know how to do that by now, right? Okay, so we are going to do the problem now with an existing problem that you've done before, and we're going to show you how to do it with the table. So we're going to decompose 2.3 moles of potassium chlorate. And I want to know how much potassium chloride is made. There's my want. And also how much oxygen is made. So I want to know two things this time as opposed to just doing one, right? So remember, we have potassium chlorate. We're going to make this. We're going to make this. So we have to write a balanced equation. And here it is. 2 moles of potassium chlorate decompose into 2 moles of potassium chloride and 3 moles of oxygen gas. All right. So the next step is you're going to have to determine the molar ratio of everything. So we're always going to reference it against the given. And the given in this case is potassium chlorate. So potassium chlorate for our molar ratios is always going to be the bottom number. And then the number that we're trying to find, or the amount we're trying to find, is the top number, right? Just like we did for the other ones, right? The given is always on the bottom when you do the conversion, and the want is always on the top. So we're going to look for the ratios, the various ratios. So the ratio of KClO3 to KClO3, it's just itself to itself, that would be 1. KCl to KClO3, so we're going to look for here. Here's my 2 of these for every 2 of these, so that's what I'm writing here. And then for the oxygen, we have 3 of these for every 2 of these, so that's how it's written here. Now we're going to fill in the information that we are in the proper boxes. So when we start out the reaction, there's no moles of KCl made, and there's no moles of oxygen made, because it says we're going to fully decompose this. But we start out in the reactor with 2.3 moles. At the end of the day, we're going to react it all, or we're going to consume it all. So we're going to change it by the same amount in a negative fashion. And at the end of the day, we're going to have 0 moles of it left. So we start with this, we're going to consume all of it, so we're going to subtract it, and then we're going to end up with 0 moles. Now how do you get the 0 moles? It's this plus this gives me this. Now we have to figure out how much of the KCl we're going to make and how much of the O2 we're going to make, because that's the change. Now how do we do that? Well, we're going to do that on the next page. Alright, so now we're going to show you how to use the tables to fill in the rest of the boxes, right? Now I've already filled in part of the boxes here, but how did I get those numbers, right? Now remember from before, we started out with 0 moles of KCl and 0 moles of oxygen because we hadn't decomposed anything yet. So we started out with this. We hadn't made any of this yet. These are my products, right? We consume all of this, so we're going to make some of this stuff. Now, how do we know how much to make? Well, we're going to use our ratio and then multiply it by our given amount to figure out what our new amount is per reactant. So for the first one, we're going to go use oxygen first, even though I've listed KCl here. Here's my model equation. Now, the model equation, if I do this, I have my dimensional analysis, just like we did before, okay? So it says for every 3 moles of oxygen made, I need 2 moles of potassium chlorate. So I'm going to start out with 2.3 moles of potassium chlorate. I put that over 1. Then I multiply it by the molar ratio of 3 moles of oxygen over 2 moles of potassium chlorate. Now why do I do it that way and not the other way? Is because we are converting from potassium chlorate to moles of oxygen. So the moles of oxygen has to be on the top. And as I mentioned before, whatever you write here has to be down here. And then I use my numbers, and I've done that. And then at the end of the day, I'm going to cross out the units that cancel, and I'm left with 3.5 moles of oxygen. So 2.3 times 3 is 7, divided by 2 times 1, which is 2, is 3.5. So that number, this number here, gets written here because it's the amount that we're changing. And since we start out with 0 moles, that number also goes here. Because 0 moles plus 3.5 moles is plus 3.5 moles. And if we did the exact same scenario for potassium chloride, it says my ratio for potassium chloride to potassium chlorate is 2 to 2. So that's a 1-to-1 ratio. So for every 1 mole of this I use, I'm going to make 1 mole of this. 1 mole of this, I'm going to make 1 mole of this. So I'm using 2.3 moles, so I'm going to make 2.3 moles. So at the end of the day, we're going to make 2.3 moles of potassium chloride. So my table is complete. I now know how much potassium chlorate I've decomposed, and I now know in moles how many moles of potassium chloride I've made and how many moles of oxygen I've made. Now if I wanted to go back to grams, I would take these numbers and multiply it by the respective molar mass. Okay, so one thing I forgot to mention on the other page is that we have a sign convention when we talk about pluses and minuses. So the convention for our class is going to be that the plus indicates that we are increasing the amount of the material, and the negative is going to signify that we are decreasing the amount of material. All right. The reason why is because when we look at the after amount, we have to understand, are we adding or subtracting to get this after amount? Because basically what you're doing is you're going to take these two boxes or these two columns or rows, the before and change, you add them together to get the after, right? So if you have a negative here, it's just like you're subtracting it. If you have a positive here, it's like you're adding it. If you just had a number here with no direction, you wouldn't know what to do with it. Do I add the 2 point? If this was there was no negative here, do I add 2.3 to this to get 4.6, or do I subtract? Now you've got to. It's easy to do when you have a sign there to kind of remind you. So minus means that we are consuming, or we're using, or we're getting rid of. Plus means that we are adding, making, something like that, right? So plus here, because these may not always be 0. In our first example, we looked at if we given an amount of reactants, how much products we can make. Now we want to go the other way. We're given the amount of products that we want to make, how much reactants do we need? And this is more representative of what industry generally does. Generally, industry doesn't make stuff and just have it sit on the shelf. The goal is to make and sell it, right? It costs money to make things, and it costs money to put things on the shelf and store them in a warehouse until they're sold. Also, if they are not sold, they have all this inventory that they now have to get rid of at a reduced cost and may lose money on. So generally what happens is when an order comes in for a large amount of stuff, that's when it's made, right? So think about making an airplane from Boeing. You don't go to the Boeing store and say, hey, I want one 747, and I want a 707, and I want a 757. No, you got to say, I need 3 747s, you can deliver them by the end of the year, and then Boeing goes out to make them. So that's what we're trying to do here, right? I want to know how much of these materials here I need to get so I can make this. Okay, so but at the end of the day, when we're done, we're going to have 0 amount of each reactant left over. And we're going to have made all of this, right? So again, the same process, write and balance your equation, determine the molar ratios, and then fill in the information that you need, that you know. So at the beginning of the process, we don't have any product. At the end of the process, we're going to have all this product, and we're going to change it by that amount. Okay, so now we want to calculate how much iron and oxygen in moles do I need to make this many moles of Fe2O3. So how do we do that, right? So we're going to calculate the amounts for each material based on the molar ratios for the given amount. Example, we're going to calculate the iron in moles, and that is equal to moles of Fe2O3, that's our given, that's our start, times 4 moles of iron for every 2 moles of Fe2O3. That's our conversion. So remember, this is like the picket fence that I've taught you guys. Okay? So again, this was our given. This is what we started with, and this is what we want. We want to know how many moles of iron, and then we have to put in the units, and there they are. And so when we do all that, we get 1.7 moles of Fe. Now, if you were to do the same thing for the oxygen, the only thing that you would change is this ratio here. And instead of being 4 to 2, it would be 3 oxygens for every 2 Fe2O3s. All right, this is for oxygen. Where do I get that? I got that from my previous thing where my molar ratios. And when we did that, that's 1.28 moles. Now we know that that's going to be the change, right? Because the change is we're going to consume it all. So this is 1.7, and this is minus 1.28. And at the end of the day, we're going to be left over with 0 because we add this to this and we get 0. This to this, we get 0. And now we finish the math, and there we go. So I need to order 1.7 moles of iron, 1.28 moles of oxygen, so I can make 0.85 moles of Fe2O3. Now, if I wanted to know in grams, I'd take this number and I multiply it by the molar mass. And same thing here. And there's everything nice and neat now. Now you have a complete picture. I know how much of each material I need. I know how much of the product I'm going to make. I know how much I'm going to consume. And remember, if I want to go back to grams, right here, I just have to multiply the molar mass to get that in there. Okay? So there's your example number 2. So let's look at another typical scenario in industry. And in industry, again, sometimes you're going to have a customer come in and say, I want to buy, let's say, 50,000 gallons of paint, of white paint, right? And you say to them, well, we don't have that much in inventory, we'll have to make it, right? And you look on your inventory as far as the raw materials and you say, well, we've got some titanium dioxide and we have some polymer and we have some of the UV inhibitor, but we've got to buy more of it, right? So in this case, the customer comes in and says, I want to buy 1.85 moles of iron 3 oxide. And your production guy says, well, we don't have enough to make 1.85 moles, but we have about 0.34 moles of iron and 0.34 moles of oxygen, right? And we don't have any moles of Fe2O3 on the in the inventory. So you're going to say, well, how much of iron and oxygen do I need to make this? And that number is going to be what you add here, what you're going to put here. And why is that? Because you need to buy this much, right? Now, here we're going to be able to put in the number here in a minute, right? So we're going to write and balance our equation again. We're going to determine the molar ratios, which I've done here, and then we're going to fill in the information that we already know. So the only thing we really know is that we're going to change the start to the end for the Fe2O3 by 1.85 moles. Everything else we don't know yet. We don't know how much this is going to change because we don't know how much it's going to change because we don't know how much we need to make this much. And then we don't know how much to buy. So we're going to use that and do that on the next page. Okay, so we filled in this here as we showed. And now I put this minus 3.7 number here. Now where did I get that? Well, I got that because I know that I'm going to have to use a certain amount of iron to make this amount of iron 3 oxide, Fe2O3. How much iron do I need to make 1.5 moles of this? Well, let's calculate it here, and I've done that right here. So here's, if you were to set this up as the picket fence like we've done before, it's moles of iron oxide that I'm given, 1.85 over 1. Then I have to multiply that by the ratio of how many moles of iron do I need from Fe2O3. So for every 4 moles of iron, I make 2 moles of Fe2O3. So when I do the math here, I get 3.7 moles. Now that's how many moles of iron I need to make exactly this amount of stuff. So why is it minus here? Well, the minus here means I actually am going to consume all of this if I want to make this. In other words, I need this amount to consume to make this. So I'm going to put that there because I'm going to, end of the day, I'm going to use that up. But look, I only have this amount so far. So at the end of the day, when I'm done, I need to buy 3.36 moles of iron. Now, why is that? Well, because I don't have enough. Okay? So, and how do I determine that? I took this number and I added it to this number and I got minus 3.36. So I have to tell my buyer, hey, you need to go out and buy 3.36 moles of iron if we want to make 1.85 moles of Fe2O3. And if I did the same setup for the oxygen, I would see that this was minus 2.78 moles. Now, how do I get that? Instead of here of 4 to 2, it would be 3 to 2. If you went back to the balanced equation, it's 3 to 2. So 3 over 2 times 1.85 is minus 2.78. And at the end of the day, I'm short oxygen minus 2.44 moles. So again, I've got to tell my buyer to go out and buy 2.44 moles of oxygen because I need 2.78 moles to make this amount of iron oxide, and I only have this amount to start with. And there it is, all buttoned up at the end. Now you have a complete picture of the reaction, the molar amounts needed or made, right? So it tells me if my boss came in and says, hey, can you make the 1.85 moles? And you would say no. And he says, well, why not? And you'd say, well, I'm short I'm short 3.36 moles of iron and 2.44 moles of oxygen. And he said, okay, so then you got to go order it, right? So again, the BCA table is a good picture of what's happening in the system at any time.